So 7.4 is our introduction on matrices and systems of equations. So we start with what is a matrix. A matrix is a rectangular array of numbers with m rows and n columns. The order of the matrix, or the dimensions of the matrix, you'll see it written both ways. Dimensions of a matrix is the number of rows by the number of columns. So we count down first and then left to right. So if I was to identify the dimensions or order of this matrix, there are 1, 2, 3 rows and then 1, 2 columns. So this is a 3 by 2 matrix. Obviously not going to be a question on your test, but you do need to know that to know how to go forward. Okay, so a lot of times you'll see it. It'll say a 3 by 2 matrix or a 3 by 3 matrix, and it becomes really important when we go to multiply these together. So it's always rows and then columns. So the first example just says, find the dimensions of the matrix. Dimensions of A would be what? 2 by 4, and B, 3 by 1. Again, easy stuff, right? An augmented matrix is one in which we replace a system of variables with just the matrix. So when you do that, you're writing only the coefficients and the constants that appear in the equation. So I'm eliminating out my variables. And it goes in order. So you're going to see some that have X and Y, obviously like this one. You're going to see some that have X and Y and Z. And then I think somebody got drunk and decided W would come after it. So then if there's 4, it actually is X and then Y and then Z. No, and then W. So if you had one with, it would end up being 5 columns, okay? The order goes X, then Y, then Z, then W. So if I wanted to rewrite this in matrix form, then whatever's in front of the X goes first. So this is -2. Whatever's in front of the Y goes next, which is 3. And whatever is constant by itself would be the last one in the row. And then the next one, it would be 5, -4, and -10. A matrix has little brackets on it, okay? So you're going to eventually get into something called the determinant, which is straight up and down lines. Make sure you can identify the difference between those. And sometimes you'll see these little dots where the equals goes, and sometimes you won't. It means the same thing. So the last ones in a row should be the constants. So this is just writing the matrix from the system or writing the system from the matrix. So for A, I would get 7, 4, -1, and 10. And then 1 is in front of the X. -5 is in front of the Y. What would be in front of a Z? 0. You want to make sure you include that. It is holding a place. So when you write the matrix, you have to have the 0. But vice versa, if I take B and I write the system from it, I don't have to include a 0Z. So this is -7x. This is my x's, my y's, my z's, and my constants. So -7 plus 2y plus z equals 4. 5x minus 3y. There is no z. I don't have to include it. Equals 15. Carlos.
If there was like 5, it would be W and C?
Yeah, so if there's a fifth column, that it would go X, Y, Z, W, and then C on the other side.
C over here.
Yes, C is always the last one. It's always a constant. We good so far? Yeah? All right, so these are all the things, the elementary row operations are the things that you can perform on a matrix. So we can switch rows on a matrix. I could switch row 1 with row 2 or row 2 with row 3. You can switch them any way you want. And that's how you would denote it, like the little arrow with 2 ends on it. And then you can multiply a row by a non-zero constant. So you can multiply a row times any number. And you can add 2 rows or multiply and add 2 rows. So you can kind of combine those 2 steps. So you're going to learn to start writing that notation down. If I'm multiplying row 2 times -3, then I would write -3 times row 2. So it looks something like that. If you are going to add 2 rows, then you could do like row 1 plus row 2. If you're going to do a constant first, like multiply 2 times row 1 and then add it to row 2, you would write that out as well. So I want you to, you're going to see in a little bit, and hopefully some of you remember. Okay, we're going to get into that process of getting these into row echelon and reduced row echelon form. And to do that, you're going to do all these row operations. As you're doing them, please note to the side what it is you're doing. So if you're adding row 1 and row 2, write R1 plus R2, then do the work. If you're multiplying row 2 times 2 and adding it to row 3, then do 2 R2 plus R3. It will help you know where you went wrong, and it will also help me when grading your test to figure out where it happened, okay? So when you look at these, we're going to, again, baby step our way in. So this just says identify the row operation or operations being performed to obtain the new row equivalent matrix. So on the left-hand side is my original matrix, 2, 4, 5, 3, negative 1, 2. And on the right-hand side is my new altered matrix. And you have to figure out what was done to get it there. So remember, we can multiply, we can add, and we can combine those two, or we can switch rows. So if you look at the first one and compare it to the second one, which row was changed, first of all? The second row, okay? So is there something I can multiply 3, negative 1, and 2 by to get 14, 0, and 13? No, so I didn't just multiply. If I combine row 1 and row 2, does it give me the new row 2? No, so I somehow altered it. The question is how? Probably, in my opinion, probably the easiest thing to do is look at that 0. How would I have gotten from a combined row 1 and row 2 to 0? I either have to multiply the top by a 4th and add it to row 2, or what's the other option? If I multiply the bottom by 4 and add it to the top, there's my new row 2. So the way you would note that is 4R2 plus R1, or R1 plus R2. That order doesn't matter. R1 plus 4R2. So in the beginning, you're just identifying what these changes are, and then towards the end, obviously, we're going to be performing these changes. Example 4 says fill in the blank or blanks, this time there's only one, using elementary row operations to form a row equivalent matrix. So first thing you have to do is identify what the change is and then perform it to the part that's missing. So how did we change the first matrix to the second? Okay, so I heard you say both, so it's good to say it. Divide row 2 by 5. Everybody sees that? Yeah? But technical terms within row operations is we don't divide, we multiply. So the way you would multiply by 5, or divide by 5 in a multiplication is by multiplying by 1/5. So I would say 1/5 times R2 is what's happening here. And if I multiply negative 10 by 1/5, what do I get? Negative 2. So you can't subtract, but you can multiply by negative 1 and add. And you can't divide, but you can multiply by the reciprocal. Same thing. Still with me? Yeah? All right, so this is called row echelon form. In a matrix, row echelon form has the following properties. Any rows consisting entirely of zeros occur at the bottom of the matrix. So if I have all zeros, it has to be at the bottom. For each row that does not consist entirely of zeros, the first non-zero entry is 1. So if I'm moving from left to right, and I have a 0 in the first field or a 0 in the second field, then the first number after that 0 has to be 1. And for 2 successive non-zero rows, so one after the other, and both being non-zeros, the leading one in the higher row is further to the left than the leading one in the lower row. So technically what you're looking for is a diagonal of 1s with zeros to the left of it, or zeros underneath it, okay? Diagonal of 1s, zeros underneath it or to the left of it. You can have numbers to the right, and you will in row echelon form, but you want those ones to be there. And again, if there's a row of zeros, it's all the way at the bottom. Reduced row echelon form has that same diagonal of ones, but zeros to the left of it and to the right of it. So below it and above it. The only non-1 or 0 numbers should be in your last column. So this is my diagonal of ones, and then I've got my 0 and my 0 above and below. Here's my diagonal of ones, and I've got my zeros and zeros above and below. So these are going to be constants, okay? They don't have to be ones or zeros. They'll be any other numbers. They can be 1 or 0, but they don't have to be. So the difference between row echelon and reduced row echelon is what happens to the right of your diagonal. Below it or left of it is always the zeros, but up and to the right in row echelon are other numbers. In reduced row echelon have to be zeros. Do we see the difference? Yes? Okay. So this says determine whether the matrix is in row echelon form, and if it is, determine whether it's in reduced row echelon form.
Can part of it be in reduced echelon?
No, so it's all or nothing. If it's not all zeros to the right, then it's just row echelon. So in this case, one thing you have is the row of zeros has to be at the bottom. That's already happening. And then you've got a diagonal of ones and zeros included in this time. You have zeros all underneath it, which means this is row echelon. But then I would need these three all to be zeros. Is that the case? No. So it's not reduced row echelon. It's just row echelon. Carlos.
Wasn't like all the ones had to be across? Like it had to be a diagonal of 1.
Yeah.
So to solve these, yes, we're not solving them yet. You're just identifying the different form. Does that make sense? So this, you would actually, if you were to solve this, there would be no z in the bottom row. There'd be no x, y, z.
Shouldn't there be a 1?
No. If there's a row of all zeros, by definition on row echelon, it has to be at the bottom, which is what's happening here. And then there needs to be, if I move, like if you look at the technical terms, if you move from left to right, the first non-zero number has to be a 1, which is happening, right? And so that is row echelon. Reduced row echelon, everything to the right of that diagonal would have to be zeros. So it's not reduced. But it is row echelon. You're thinking of Gaussian elimination and Gauss-Jordan, which is the way to solve systems using row echelon and reduced row echelon. We at this point are just identifying which ones they are. Does that make sense? Yep.
For reduced, obviously this is not reduced, but
Yep.
for reduced, isn't all the ones on the right supposed to be not like a constant, non-zero?
No, for reduced,
So
for reduced, these would be zeros and these would be zeros. These can be zeros because you can have a variable that's a 0. You can have an x that's a 0 or a y that's a 0. Okay, so now we're going to work our way through row echelon form. So we are taking a matrix and we are getting it into row echelon form. Not reduced row, just row. So our goal here is to get a diagonal of ones and zeros underneath. So I'll give you some tips. You don't have to do it the way I'm about to do it, okay? But sometimes it's hard just to get started. So I tend to work in a pattern. I tend to first get a 1 in this location. It's already there, right? If it wasn't, that would be my first goal. Get a 1 where that is. So I would say that that's step 1 for me, typically. Then I go to work my way down and right with the zeros. So I would say step 2 for me is here, and I want what to be in that spot if this is row echelon? 0. So how, using the row operations that I know, could I get that spot to be replaced with a 0? I can't multiply by 0. That would be so easy. Can't do that.
Can you add 2?
If I add row 1 and row 2, what happens? Remember, I can't add numbers. So my options are multiply by a number, right? With me? But it has to be non-zero, so I can't multiply by 0. My second option is add 2 rows. If I add any of those 2 rows, will they cancel out, giving me a 0 in that spot? No. My third option is multiply and add. So think about this in terms of your systems, right? How would you have canceled out your x's? Because that's what we're doing.
So you multiply the first one by 2 and then add it to
Okay, you're both right. So I heard multiply the top by 2 and then add it to row 2. And then Carlos, you saw multiply the second row by a half and add it to row 1. Yes? Totally works. Avoid the fractions as long as you can is my tip. So I would multiply row 1 by 2 and then add it to row 2. Do we see that? But I'm replacing row 2. I'm not replacing row 1. So I'm going to do 2 times row 1 plus row 2. So I'm going to multiply row 2. I'm actually going to write it out so you can see it. And this is where those negatives come back to haunt you. So be really careful when you write this out. So that's row 1 and row 2. I'm going to multiply row 1 by 2 and add it to row 1. Now I can replace either row 1 or row 2 with this because those are the 2 that I have used. I'm going to say that again. I can replace either row that you add together with your new row. So I could either replace row 1 or row 2 with this. But row 1 already has the 1 in place. I don't want to replace row 1. Does that make sense? So I'm going to replace row 2. So my new matrix would be 1, 1, 0, 5, 0, 1, 2, 0, 3, 6, 7, 14. Same goal, diagonal of 1s, 0s below them. So again, I'd work through the 0s before I start worrying about the other 1s because sometimes you can change it to a 1 and lose your 0. You want to keep the 0. So my next spot would be this one. I would want to make that be replaced with a 0. I can't multiply by 0. I can't subtract 3, right? I can't go across and subtract. So what is a way to combine it with another row in which it would cancel out that 3?
Multiply the top by -3 and add them.
Good. So -3, row 1 plus row 3. So this time I'm going to multiply row 1 by -3. That's -3, -3, 0, -15, and 3, 6, 7, and 14. 0, 3, 7, -1. And again, I can replace row 1 or row 3 with it, but row 1's already set the way I want it to do. Row 3 is what I'm trying to replace. So 1, 1, 0, 5, 0, 1, 2, 0, 0, 3, 7, -1. Again, same goal. Diagonal of 1s, 0s underneath, and I have one more 0 to replace. So think about what could happen, because there's 2 ways to get a 0 where that 3 is. What's one way?
Multiply the second row by -3 and add them.
Good. Multiply the second row and add it to the bottom row, right? That would cancel it out. I could also multiply the top row by a -3 and add it to row 2 to row 3. But what happens to the 0 I just tried to get?
And make it a negative.
Exactly. So when you go get your last 0, you have to use row 2 and row 3. I'm going to say that again. When you go get that last 0, you have to use row 2 and row 3. If you bring back row 1, you will lose the 0 that you just got in this position.
Every time.
Every time. So I'm going to do -3, row 2 plus row 3. Multiply this one by -3. 0, -3, -6, 0, 0, 3, 7, -1. and I get 0, 0, 1, negative 1. And again, I could replace row 2 or row 3 with that, but row 3 is what I'm working on, so I leave 1 as it was, I leave 2 as it was, and I replace row 3. My goal, diagonal of 1s, 0s underneath. This is row echelon form. Yep.
Would you hit the 1? No, 0, 0, 1, 2, negative 5.
0, 1, 2, negative.
0, 1, 2, 0.
That came from this. So I did 2 times row 1 plus row 2. And then replace row 2 with it. Carlos.
That's just coincidence that it's like all ones across. Because I thought only the first one had to be 0, and then the ones on the bottom had to be. I thought the only first one had to be 1, and the ones on the bottom had to be 0. Like, why are the rest of them 1?
No, in each row, moving from left to right, the first non-zero number has to be 1. You mean that diagonal of 1s?
Yeah.
It has to be 1s.
What about the one at the top?
So this is row echelon, not reduced row echelon. Reduced row echelon, I would keep working at, I would make these 0s. But all it asked me to do is get it in row echelon. And I'm not even solving it yet. Like, you're about 3 steps away from actually solving this system. We're not there yet. Okay, you're just right now just getting it into row echelon. Isabella.
What's the difference between this and when it's all zeros?
So all zeros, and what happens is, what happens after this? After this, I convert that into a system, and I solve it using back substitution. I take the bottom, I plug it into the second one, I take the second one, I plug it into the top. When you get it into reduced row echelon, where there's zeros all on top, you already have an x equals a number, a y equals a number, and a z equals the number. So you work further on the matrix side, but you do almost no work to get it out into a system. Whereas with row echelon, where you still have numbers above the 1s, you would then have to take z, plug it into the y plus z equation, and then take the y and the z and plug it into the top equation. So the difference comes what I have to do after this. But for right now, you're just getting it into that format. You're not even solving it yet. Marissa.
So the diagonals have to all be 1?
Correct. In either form, the diagonals have to be 1 and zeros underneath the diagonals. The difference is this, I'm done once I get there. Reduced row echelon, I would have to work to get zeros above it, which we're going to do.
What if you got it like that? What if they were all zeros at the bottom?
It probably won't happen when we're solving a system. It's still row echelon, but it probably won't happen when you're actually solving the system.